All right, so what I want you to do is I want you to consider the path of an object along the curve y equals negative 2x squared plus 9x plus 20. And what happens is that this equation relates the height of the object with respect to time. So we have a picture right here where on the x-axis we have time and on the y-axis we have the height. Although this equation tells you where the object has been vertically, it doesn't tell you where the object was at a given point x comma y. So basically it doesn't tell us anything about the horizontal movement of the particle. Because a lot of times when projectiles are fired up, not only do they go up, but they kind of go over some. So you don't have any knowledge of how far it's going over. So what we're going to do is we're going to introduce a third variable t that's called a parameter. So what we do is we let x equal t, and then if x is t, then y would equal negative 2t squared plus 9t plus 20. So, and a set of equations where one is x equals something and one is y equals something is called a set of parametric equations. And if you evaluate both equations for a value of t, then it gives you the coordinate of the position of the object after t seconds. So, for example, how far has the object traveled horizontally and vertically after 2 seconds? Well, after 2 seconds, it will have traveled horizontally 2 units. Because in this case, x just happens to equal plain old t. And it will have traveled vertically, whatever you get when you plug a 2 in for t in the y equation, which happens to be 30. Okay, so by plotting the points in the order of increasing values of t, the curve is traced out in a specific direction, and that's called the orientation of the curve. So that first example was just kind of an example of how you can change a regular equation into a parametric equation. Most of the time, they're going to give you a set of parametric equations. So they're just going to give you x of t equals and y of t equals. A lot of times, they'll give you a range of t values to deal with. All right, so what we want to do here is we want to sketch the curve and indicate its direction. So what I'm going to do is I am just going to make myself what normally would be a little t chart, but now I'm going to have 3 columns because I have t, x, and y. And t are all the numbers between negative 1 and 4, but I'm just going to use the whole numbers for the sake of evaluating this. So when t is negative 1, x will equal 3, and y will equal 0. And when t is 0, x will equal 0, and y will equal 1. Are you all cool with plugging these points in? Okay, then I'm going to go ahead and just tell you that when t is 1, x is negative 1, and y is 2. When t is 0, x is 0. I'm sorry, when t is 2, x is 0, y is 3. When t is 3, x is 3, and y is 4. And when t is 4, x is 8, and y is 5. So what we're going to do is we're going to plot just the x and the y values in ascending order of t. So basically, as t increases, we're going to plot the x and the y coordinates. So we're starting with the point 3, 0. And then we're going to go to 0, 1. And negative 1, 2. And then 0, 3, 3, 4, and 5, no, 8, 5. Yeah, we're literally just plotting normal x, y. And then we're going to connect the points into a smooth curve. and I'm going to indicate the direction that my points were plotted by putting little arrows. So those little arrows indicate that I started at the point 3, 0, and then came around to the point 8, 5. And because t was just between -1 and 4, I didn't put arrows on the end. I just want that graph in between those two t values. All right, if you have a set of parametric equations, you can convert it back to the corresponding rectangular equation, which the rectangular equation is the same thing as the function equation. So basically just back to the normal type of equation that you're used to, y's and x's. Y equals blah, 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 x. All right, so the way that you do that is you eliminate the parameter. All right, I'm working under B, but I'm going to use some of the space up here so I can see the equations. My two equations are x equals t squared minus 2t and y equals t plus 1. Any thoughts as to how I can get rid of the t's in those two equations? Yeah, I kind of use a system of equations. I can solve one of the equations for t and then substitute it back up into the other one. Do you want to solve x equation or y equation for t? Definitely y. So t would equal y minus 1. And then I'm going to go back up to x. And everywhere I see a t, I'm going to put in y minus 1. And I shouldn't have used the rectangular equation. Basically just means x's and only x's and y's. Sometimes it will be a function, sometimes it won't. And the fact that what we had just graphed, was that a function? No. So we're not going to be able to solve for y very easily, and we're not ever very interested in simplifying things, so I've done exactly what they've asked me to do. I've eliminated the t. I have an equation that just has x's and y's in it. Okay, so that's kind of a review of what parametric equations are. Now let's get into the calculus of it. I actually think the calculus part of the parametric equations is easier because really all you're doing is taking the derivative of them. All right, a curve C that's represented by x equals f of t and y equals g of t. Okay, that just means that you have a set of parametric equations. Okay, x equals something in terms of t, y equals something also in terms of t. It's called a smooth curve if f prime and g prime are continuous on I and not simultaneously 0, except possibly at the endpoints. Okay, the bottom line is that there are no sharp turns or points. Okay, if they refer to a smooth curve, it means you have no cusps or points, like really sharp points. That's the main thing you need to get out of that. All right, parametric form of the derivative. If we have x equals f of t and y equals g of t, then the slope of c or the slope of the curve at the point x comma y is still given by dy dx. Slope is always dy dx. You're used to that. But when you take the derivative of y, if your equation is in terms of t, then that's going to equal dy dt. And when you take the derivative of x, if your independent variable is t, then that's going to give you dx dt. And if you have, it's easier to see if you write it like this. So dy dx is going to equal dy dt over the derivative of x with respect to t. And when you take dy dt divided by dx dt, it's the same thing as dy dt times what? Right, dt over dx. So what happens? Right, the dt's cancel and you're just left with dy dx. Yes. So find dy dx for the curve given by x equals sine t and y equals cosine t. So we're basically trying to find a formula for the slope of those parametric equations. So dy dx, or dy, is going to be with respect to t. So dy dt equals, derivative of cosine is negative sine t. And dx dt equals what? Cosine t. So dy dx is dy dt over dx dt, or negative sine t over cosine t, which might be nice to write as negative tan t, but you don't have to. So you're literally taking the derivative of y with respect to t, taking the derivative of x with respect to t, dividing the two things. Okay, now the higher order derivatives are just as easy, and what I mean by that are the second derivative, the third derivative, etc. But the formula is a little bit confusing. This means, so d squared y over dx squared means the second derivative. So your second derivative. Well, the second derivative is the derivative of the first derivative. Y'all cool with that? All right, well, in terms of so if you're taking the derivative of dy dx, then you have to take the derivative, and dy dx, remember, is in terms of t. So you have to take the derivative of dy dx in terms of t, but then you have to divide by the by dx dt. Let me take the problem that we just did. We came up with the problem before that dy dx equaled negative tan t. Is that right? All right. So the second derivative equals the derivative of dy dx, which the derivative of negative tan will be negative secant squared t, and then over the original dx dt. And the original dx dt was cosine t. And if we wanted to, we could write this as negative secant cubed, or negative 1 over cosine cubed. It's like take the derivative of the previous one and then divide it by the original dx dt. So like for the third derivative, let's just do it again. So for the third derivative, I'm going to take the derivative of the last derivative, which would be what? Negative 3 secant squared t Yeah, because negative secant cubed is the same thing as basically negative 1 times the secant of t quantity cubed. So we just need to use the chain rule to take that derivative. And the chain rule would be 3 times negative 1 is negative 3. You decrease your exponent, and then I have to take the derivative of secant, which is secant t tan t. And then divided by the original dx dt. All right, so if we really wanted to, we could simplify this into probably something else, but I'm not really interested in that.